Until now, our main unknowns were node voltages. Today we switch to a different viewpoint, mesh currents. Instead of writing Kirchhoff's current law at nodes, we assign one loop current to each mesh and apply Kirchhoff's voltage law around each loop. This works best for planar circuits where the loops are clearly separated on the page. The key rule is simple. On a shared element, the branch current is the algebraic difference of the two neighboring mesh currents. Here is the core idea behind the mesh current method. In the left picture, I1 and I2 are not branch currents yet. They are imaginary loop variables that circulate around the two meshes. In the right picture, the actual resistor currents appear. For the shared center resistor, the downward branch current is I1 minus I2 if both mesh arrows are chosen clockwise. That shared term pattern is what creates the coupling between loop equations. And if the solved current comes out negative, that only means the real current direction is opposite to the arrow we assumed. Now the first worked example. The circuit has three meshes. We choose all three mesh currents clockwise and call them I1, I2, and I3. The left loop contains the 28-volt source, the 6-ohm resistor, and the shared 2-ohm resistor. The middle loop contains the shared 2-ohm resistor, the 8-volt source, and the shared 4-ohm resistor. The right loop contains the shared 4-ohm resistor and the 12-ohm resistor. The quantity we want is the branch current I through the 2-ohm resistor directed upward. Start with loop 1. As we move clockwise, we see a 28-volt source and two resistor drops. The 6-ohm resistor carries only I1, but the 2-ohm resistor is shared, so its branch current is I1 minus I2. So the first KVL line is negative 28 plus 6I1 plus 2 times I1 minus I2 equals 0. Now distribute the 2-ohm term carefully. 2 times I1 minus I2 becomes 2I1 minus 2I2. That is why the I1 terms add to 8I1, and the first mesh equation becomes 8I1 minus 2I2 equals negative 28. Now loop 2. Both resistors in this loop are shared, so the drop terms are 2 times I2 minus I1 and 4 times I2 minus I3. The 8-volt source also appears in the loop, so loop 2 gives 2 times I2 minus I1 plus 4 times I2 minus I3 plus 8 equals 0. When you distribute those shared terms, you get 2I2 minus 2I1 plus 4I2 minus 4I3 plus 8 equals 0. Now the I2 terms combine into 6I2, so loop 2 becomes negative 2I1 plus 6I2 minus 4I3 equals negative 8. For loop 3, only the 4-ohm resistor is shared, so we write 4 times I3 minus I2 plus 12I3 equals 0. After distribution, that becomes 4I3 minus 4I2 plus 12I3 equals 0. So the final loop 3 equation is negative 4I2 plus 16I3 equals 0. Now solve the three equations together. From the third equation, I2 equals 4I3. Substitute that into the second equation and then use the first equation. The results are I1 equals negative 13 over 3 amperes, I2 equals negative 10 over 3 amperes, and I3 equals negative 5 over 6 amperes. All three mesh currents are negative, so the actual current directions are opposite to the clockwise arrows we assumed. The ask branch current through the 2-ohm resistor is upward, so it equals I2 minus I1. That is negative 10 over 3 minus negative 13 over 3, which gives exactly 1 ampere upward. That is the full workflow of the mesh current method. First, assign one loop current to each mesh. Then, write Kirchhoff's voltage law around each loop. On every shared element, use the current difference between neighboring meshes. Finally, solve the linear system and interpret the sign of each result. A negative mesh current is not a mistake. It only means the true current direction is opposite to the arrow you started with. In the next lesson, we will continue with more mesh analysis examples.